All right, let's talk about caching. We all use it, right? It's our go-to for making our apps feel snappy and responsive. But what happens when that speed comes at a price? A price of correctness? Today, we're not just talking about basic caching, we're opening up a whole toolkit for building systems where your data is not just fast, but provably consistent. I want you to really think about this for a second. What if the data your application is showing to your users is just plain wrong? See, stale data from a cache isn't some minor glitch. It can cause some of the most infuriating, impossible to reproduce bugs you will ever face. The stakes here are incredibly high. And this quote? This gets to the absolute heart of the problem with the most common pattern out there, cache aside. It just hits the nail on the head. As developers, we try our best, right? We write our code to clear the cache whenever we update the database. But what about that one-off admin script someone runs? Or a direct manual database fix to solve an emergency? Your application code isn't the only thing in the universe that can change your data. So this hidden flaw, it's a classic race condition. It's one of those bugs that pops up when the timing of two events goes horribly wrong. Just imagine this. Your code updates the database. Perfect. Then it immediately tries to invalidate the cache. But what if the network just blips for a fraction of a second right then? Well, now your database has the truth, but your cache, it's stuck serving a lie, and it might just keep serving that lie forever. So if we can't trust our own application code to get this right 100% of the time, what can we trust? Well, how about the database itself? This leads us to what you might call the nuclear option for consistency, Change Data Capture, or CDC. It is, without a doubt, the most robust way to guarantee your cache stays perfectly in sync with your source of truth. You see, the real power of CDC is that it completely bypasses your application code. It doesn't care about it. Instead, it taps directly into the database's internal transaction log, something often called a write-ahead log. You can think of this log as the database's own indestructible private journal, where it records every single change that has ever happened. CDC just listens to that journal. Okay, so let's walk through what this looks like in practice. You've got a tool, say Debezium, and its one job is to watch that database log. As soon as a row changes, Postgres itself emits an event. Debezium grabs that event and immediately pushes it onto a super reliable message queue, like Kafka. Then from there, a tiny dedicated service we can call a cache invalidator just picks up the message and tells Redis, hey, delete this stale key. It's a rock-solid, completely decoupled pipeline. But, of course, there's a trade-off. There always is. On the one hand, you get this undeniable, bulletproof consistency. If you've got dozens of microservices all touching the same data, this is honestly how you sleep at night. But on the other hand, look at the complexity. You are now running and maintaining significant new pieces of infrastructure, like Debezium and Kafka, and that is a serious operational investment. So what if CDC is just overkill for your needs? That's totally okay. It really is a big hammer for a big problem. Let's open up the rest of our toolkit and look at some other patterns that you can use for different kinds of jobs. So, first up in the toolkit is the read-through cache. With this pattern, your application logic gets a whole lot simpler. It just asks the cache for a piece of data. If the data isn't there, a cache miss, the cache itself is now responsible for going to the database, loading the data, storing a copy, and then finally returning it to your app. The biggest pro here is obviously cleaner application code. But the trade-off is that your cache is now tightly coupled to your database. And that very first user who asks for a missing key, they're the one who pays the price, waiting for that whole database trip. Even worse, if a really popular item expires, you can get what's called a thundering herd, where hundreds of requests all hit the cache at once, and they all trigger their own separate, expensive call to the database. Not good. Okay, next tool in the box, write-through. This pattern kind of flips the logic, but for writes. Your application writes data directly to the cache, and then the cache, in that very same operation, synchronously writes that data through to the database. The whole thing isn't considered done until both are updated. So the benefit here is crystal clear. Your cache is basically guaranteed to be consistent with the database. No more stale data issues on writes. The cost? Well, every single write is now slower because it has to make 2 network hops. And you've just introduced a new single point of failure. If your cache is down for some reason, all of your writes start failing. Now, for those times when write speed is absolutely everything, there's write behind, sometimes called write back. With this, your application writes to the cache and gets an immediate "OK" response. It's incredibly fast. The cache then takes on the job of writing that data to the database sometime later, asynchronously, maybe even in big batches. The performance gains here can be massive. I mean, huge. But just look at that top con, it's highlighted for a reason. A very high risk of data loss. If that cache server crashes before it has a chance to flush all those writes to the database, that data is just gone, vanished into thin air. This is exactly why you never, ever use this pattern for critical data like payments or user accounts. All right, our last tool is a really clever optimization called Refresh Ahead. The whole idea is pretty simple. Instead of waiting for a super popular item to expire and making some unlucky user pay for that cache miss, the system is smart enough to proactively refresh that data before it expires. This is just perfect for hot data, or data that's really expensive to generate. Think of a complex report that tons of users are looking at all day. By refreshing it just ahead of time, you make sure that the user experience is always fast, completely eliminating that painful wait on an expired key. So, we've just looked at a whole toolkit of patterns, everything from the sledgehammer that is CDC to the fine-tuning of Refresh Ahead. But here's the thing, picking the right pattern, that's only half the battle. The next, and honestly much harder challenge, is knowing if the thing you built is actually working. So you did it. You designed the system, you wrote the code, you deployed it. But now what? How are you supposed to debug a race condition that only seems to happen once every million requests? How do you prove that your system is actually consistent when it's under heavy load? Well, the answer is observability. As the source material makes really clear, these kinds of cache bugs, the ones that depend on millisecond timing, are nearly impossible to reproduce on your laptop. To really understand what's going on in production, you need the right metrics. And I'm telling you, cache hit rate is not enough. You need a much deeper view to spot anti-patterns and make the right trade-offs. And that really leaves us with the final and maybe the most important question of all. It's one thing to design a system that should be consistent. It's another thing entirely to prove that it is, day in and day out under real-world load. And that, right there, is the difference between hope and engineering. Thanks for joining this explainer.